morning to the last day. We've got our distinguished lecturer, Jack Snoeyink, can give us a talk about computational thinking.
I'm afraid it might be the extinguishing lecturer or something. When I looked at the schedule and saw how many things you were doing before early Friday morning when I was supposed to talk, I decided that I wasn't going to try to give any sort of, large ideas or overview of all of, theory of computing science and scientific computing. Instead, I wanted to give a bunch of little vignettes, and I decided to make it even smaller and make it bumper stickers. So what I want to do is give you some bumper stickers. And I haven't used Google Presenter before, and so I'm trying to. This is very interesting. I can put the speaker notes here, but my advance button is still over there, unless I use the keyboard. All right. So roughly, these things are from scientific computation, software design, and CS theory. And this is less of an outline than just a bunch of keywords. And as I was putting down keywords, I realized that this is a symbol of a paradigm shift. If you're used to biology or genomics, proteomics, all of these omics, when you start talking to computer science people, you switch the suffix. So omics roughly means the study of a whole set. The genomics is the study of all of the things about genes, proteomics. Eyes is something we tack on to a noun to turn it into an action. And so I'll talk about linearize, minimize, normalize, optimize, analyze, localize, visualize, and all of these things that we turn into actions. And so this is why when you're talking to computer science people, you're talking to methods people. And one way to this is going to drive me nuts here. But one way to sort of underline the difference is, if you think of real science versus computer science, right? Any science with the name science in the name of the science is not a science. But in real science, when one discovers a fact about nature, it's a contribution per se, no matter how small. This is quoting Fred Brooks, who's the founder of the department across the street. Since anyone can create anything new in a synthetic field, that alone does not establish a contribution. Rather, one must show that the creation is better. And so the job of the computer scientist is to create things. It's easy to create new programs, but show how ideas lead to the creation of better programs and show that the programs are better than what could previously be done, what would be done with other ideas. And so that aspect of showing something better is an important thing. Matt showed this as his illustration of a function the first day. One of the things that I emphasize is when you're telling me about some procedure, don't start with the steps of the procedure. First, let's make sure that I know what you're talking about. So tell me what the input is and what the desired output is. Okay, but before you start telling me what you're doing. And this is something that is actually going to be a recurring thread through the talk of, what we're often doing is trying to define exactly what we're doing. When you try to communicate with somebody and agree on the definitions, you learn more about what you're doing yourself. When you try to communicate with a computer, you have to really get the definitions down very precise, because the computer is so stupid it's going to do exactly what you tell it. It has no latitude for interpretation, and so you really have to refine your definitions before you decide of what you're doing, before you decide exactly how you're doing it. And that's a lie, of course. As I said at the beginning, any education is a process of telling lies and then refining them, because what we do is we make some definitions and we do something and we find out where things don't quite fit, or how we could get some ideas of how we could improve it, and we keep going in a spiral, constantly being able to improve things, getting better and better ideas of what should be our input and what should be our output. And the second thing, what's always going to remain true while the program is running? In computer science we call this the invariance. What are the properties that we want to have be true the whole time? because those two things basically tell us how to write the code, how to write the steps, deciding what steps it performs. So, by the way, it's the decisions that you make in 1 and 2, those are the things that you want to document, because those are the engineering decisions that make your thing better, or the things that, when you want to try to improve, you can go back and question. So document the decisions that you make about the input and output and about the invariants that are going to hold. The steps are just will often follow from those decisions, and so the other thing to look at in this machine as a function, taking inputs to outputs, especially if you're thinking of things like scoring functions or classification, many of the tasks that you do with Rosetta. One way of understanding a function is to look at the space of all possible inputs and look at what are the inputs that the thing will give the same score to. So what things, if you change things in the input, will not change the score? That's one of these sort of invariants, and that is often helpful. That's a theme that will come up a couple of times. All right, yeah. Please ask me questions. Some of this will be philosophy, and some of this will be very picky details. So.
Okay, well, this is more philosophical.
Yeah. No, it's so far the slides have only been philosophy. So.
So for two invariants, and always hold. It's hard in a biological context to be described like a biological process.
Right.
Things like two.
Right. And
inevitably, you can almost never say this residue has to be in contact with that residue for this thing to happen, because there's noise, the thing is bouncing around.
Right.
So it's kind of a very unnatural thing from a biological perspective.
I wouldn't say it's unnatural still, because, I mean, the idea of mathematical invariants, things that are always true, may seem a little bit unnatural. However, there are certain things, I mean, so physical invariants, conservation of mass, some of these sort of things. All of these things come from symmetries in the system. So this is Emmy Noether's contribution to mathematical physics. And these are the things on which a lot of the mathematical work is based on. And then in biology, you want to find things that, it may not happen all the time, but it sure happens a lot. And so that's, sort of defining, those are the things that you're looking for, and the things in which you start to build your theories around, even if they're, sort of more statistical validity than precise mathematical validity as it would be for sort of the physical laws. And then, of course, the physical laws come into question as well. I mean, things are only valid at some level of approximation, and so it's really it is a common thing. It reveals commonalities and differences, because in computer science, when I'm talking invariants, I want some statement that I can prove is true and is always true, because then I know my program is doing what I meant it to do. Now, it may be working with imprecise data, but at least what I know is it's going to give consistent, reproducible results if I give it the same data. And that's another. We'll get back to that. But yeah, so okay, here we go. All right. Let me say just a few words about that. Sort of leads into input data error imprecision. I mean, this is your largest source of error, is the imprecision in the experimental data that you feed into the program. Yet it may be important to track this error quite precisely, because then you can get an understanding by a precise understanding of the mathematics and programming that you're passing it through, of how that error propagates through to the output, so how much reliability you have in it. And you don't want the computer to add in more sources of error in general. There are several sources of error. Floating point error is one. Computer represents only a finite and unevenly spaced set of real numbers. We think that we have the real numbers, but we don't. Truncation error. There's processes or series that you stop early when the error is small enough, or as things are approaching convergence. You never run it through all the way. And there's been a lot said about programmer error, and the biggest error is failure to test. because the computer does not know your intentions until you write unit tests that show what your intentions are. So keep pounding on tests. Mika can say a lot about error sources, but let me just give one quiz. Which arithmetic function is the most dangerous for creating numerical error in floating point arithmetic? How many think addition? How many subtraction? Multiplication? Division? It's addition. The same as subtraction because, addition of a negative number. I say it's addition because subtraction seems the most dangerous until you realize that addition is hidden subtraction, so you don't expect it to cause errors. No, it's actually addition. Multiplication and division are quite safe. I mean, you don't want to divide by 0 and things like that, but those create a fairly small relative error, and usually error in computer science we worry more about relative error than absolute error. The problem with addition, or let's phrase it as subtraction, is suppose I have 16-digit numbers. Okay, I calculate a couple of 16-digit numbers that are almost the same, and I subtract them. If their first 10 digits agree, and I cancel out those 10 digits, I'm left with 6-digit numbers. I lose almost all of my precision by subtracting nearly equal numbers. That's the biggest way you lose precision in doing floating point arithmetic, subtracting nearly equal numbers. And so if you got something like you're computing a polynomial, standard way of, I'm sorry, this is my first time using Google Presenter, and I don't understand why the arrow button is here. Okay, so standard polynomial. There's no subtractions, it's just addition, the most dangerous operation. And some multiplications, those aren't so bad. The exponents are just repeated multiplication. You shouldn't evaluate polynomials in the way you normally write down polynomials. Okay, because what do you have to do? You've got to do all these multiplications to get x to the n. So you've got to raise x to a power, and then you've got to multiply by the coefficients. And then you've got to do the additions. Even worse, what you're doing is you're taking x to the n times some coefficient plus x to the n minus 1 times some coefficient. And so you're taking two numbers that could be quite big and adding them, but those coefficients may have opposite signs, so you may be getting a lot of cancellation. For both reasons of reducing the number of multiplications, maybe not so important these days unless this is in the inner loop, and preserving significant figures, here's the way you ought to think of evaluating polynomials instead. Let's rewrite this so that this polynomial px is a polynomial using the coefficients from an to a1 times x plus the a0 coefficient. Okay, and it's easy to see how to continue this pattern. So the pn1 polynomial is a polynomial on coefficients an to a2 times x plus a1. All the way down to the pnn is just the polynomial with the coefficient an and no x's left anymore. So now you can evaluate this polynomial by just adding on the coefficient, multiplying by x, and then get the next polynomial, add on the next coefficient, multiply the whole thing by x, etc. You wind up with less multiplication. You don't have to worry about exponentiation. And you don't let those powers get the numbers too big and then cancel them off. And so this tends to be much more robust in practice. You can still have problems. You can still concoct nasty examples, but especially for the sort of interpolation that we use polynomials for, this is the thing to do. And the other nice thing about this is take the derivatives. So the derivative of this polynomial, you just use the chain rule here, it's the derivative of the pn1 polynomial times x plus pn to the n plus 1. Well, this we calculated over there anyways. So this is sort of like a constant. once we've calculated the polynomial, we get all of these constants from here, and then this is exactly like doing the polynomial itself. And so here's your program. Input, you take the polynomial coefficients. Output, produce the polynomial and the evaluation of the derivative at a given x. I forgot to put x as part of the inputs. And it's just a short little piece of code here that will give you the polynomial and derivatives. This is the kind of thinking of questioning assumptions of why should I write the polynomial this way? If I write it in this way, then I get better accuracy, and I get the derivative for much cheaper. I don't have to do as much computation. Question?
I had a question on the previous slide, actually.
This is known as Horner's rule, by the way. The previous slide, yes.
Yeah, just about error. One thing that often comes up with Rosetta is like, well, you have some protein and some conformation,
Right.
and you do some docking on it or whatever. And then I've often heard, well, you should just move the protein a tiny, tiny bit and dock again, and maybe you'll get better results or something like that, or maybe not. And so, is that because of numerical error? Is that because Rosetta is not precise enough? I mean, it just seems like a little magical that.
Yeah.
Disturbing that you should perturb a ligand slightly and you could get all different things. So
Yep. So let's get to that in just a second. What's going on there? Part of what's going on there is that you think of these energy functions, but what's going on is there's algorithms that are doing the calculations looking for minima, and they get stuck in local minima. And so if you start in slightly different places, they'll take a slightly different path. We'll get stuck in a different local minimum, and hopefully these are close. So why does this happen? So root mean squared deviation. Your input is 2 points for 2 structures that correspond. You want to output the minimum RMSD, the root mean squared deviation, which is basically you want to transform one of the points by rotation and translation, so that when you take the differences, you square them and take the square root, that this is as small as possible. Okay, it's a standard way of superimposing 2 things. Why do we use the square? Why do we use least squares? What's linear? I've got a square root, I've got a quadratic. There's nothing linear there. The distance is not linear. Distance is Pythagorean theorem says I've got squares and square roots. So why should I use the squares? Why shouldn't I use the absolute value? That'd be much more linear.
Maybe the distribution of the error will be normal.
Maybe the distribution of the error will be normal. So, yeah, I don't know about that.
Easier to calculate the derivative for this?
It's the derivative. Yeah, I mean, a lot of times you get answers, oh, it's properly weighs outliers and all of this stuff. That's all bullshit, okay? The reason we do this is because we're trying to minimize. And when you take a derivative of something that's quadratic, you get something that's linear, okay? We can get rid of the square root by just, if we want to minimize something that's the square root, we just square the thing. It's got the same minimum, okay? So then we have something quadratic. Then we take the derivative, and we get something linear. And so the reason you do least squares is, well, we know how to solve simultaneous linear equations. Just write it, this is written in matrix form. And if you get rid of the square root sign and just write this as simultaneous, or as a quadratic, take the derivative, we'll find out where the derivative is 0. That's just a simultaneous set of simultaneous linear equations. And in matrix form, you can just write out what the answer is. Don't actually compute inverse matrices. You call packages that will compute this value for you without computing inverse matrices because it's much more numerically stable. You don't have to know about that, other than that there are very good packages for doing all of this sort of stuff. So the reason we use least squares is because it takes a minimization problem. When you take the derivative, it becomes linear. And this theme comes up many times in the numerical software, is you take your mathematics and you do linear approximations to it and use that within the computer. So this problem also indicates that it's really good to use the right representation when you're doing this. When you're doing superposition, I mean, if you just look up in the linear algebra book and look at point correspondence problems, they'll tell you to just do the solution that I just said. Here the problem is now how do you find out what t is? What is this transformation? And you can use singular value decomposition to get the matrix that will represent the best transformation from one to the other. But if you do that, you have to worry about getting reflections. So if you just say, take a sort of a rotation matrix, transformation matrix, you have to then check the determinant of your matrix to make sure it's positive and make sure that you haven't actually flipped the molecule. And I've done this myself where I'm getting really good alignments and I try and superimpose them and they look terrible. And actually the right way to do this is to use quaternions. And I understand that Wednesday there was a debate about why whether Rosetta should be using quaternions. This code should definitely be using quaternions, and is, because this is something that you can write and encapsulate, and nobody has to know that it's using quaternions to do the superposition. But quaternions are something that will just give you rotations and translations, and they will not give you the reflections, so it won't be part of the solution space. And Berthold Horn has a nice 1987 paper that's linked from that link, and then there's the Kutzis, Dill, and I forgot the Silk paper from '04 that the biochemists know more about. It took them a while to discover that quaternions were the right way to do things. When it comes down to pose, I can live with rotation matrices because people more readily understand rotation matrices than they understand quaternions, unless there was a good library in Rosetta that would do all the rotations and hide the fact that it was using quaternions. It actually, might be a good project, Andrew. Things would be a little bit more efficient with quaternions, unless you're switching back and forth between rotation angles and quaternions often. If you can just leave it in quaternions, then it's good to keep quaternions. But okay, another example of linearization, Newton's method, when you're looking for the zeros of something. The Newton's method, your input is a function and its derivative, and some initial guess at where you want to find the zero. And your output is an x so that f of x is approximately 0. And the idea is you're just going to guess x by extrapolating from what you know. You know the value of f of x, and you know the slope at f of x. And so you say, well, I think my function is that line that goes through there. And if it were that line, then here's my next guess, xn plus 1. And as long as your function is well behaved and you start in the vicinity of a root, then you'll get there very quickly. It actually has quadratic convergence. It's very nice to look at the Taylor series expansion of this and see how this expression nicely cancels out terms so that it's the second order term that dominates. Just another example worth knowing if you ever want to improve the accuracy of some numerical method. You try to use Newton's method if you're dealing with something with a single variable. And this idea is what is extended in the various techniques for minimization, steepest descent, conjugate gradient, other things. The idea here is we take as input a function, and we take the Jacobian, which is basically just the matrix of all the partial derivatives of this function. And we take some current guess, and then I want to output an x that minimizes f of x. And the idea is guess what figure out what the next guess is by walking in a direction of steepest descent to give you the next place. So this, if your function is very nasty and has lots of local minimum, then you get this phenomenon that different starting places are going to give you different paths, and different algorithms will give you different paths. Different step sizes will give you different paths. this is something that you cannot really avoid when you're dealing with complex functions like that. There's nothing free, okay? Not everything is easy. And you should think of this as job security. I certainly do as a computer scientist. But one of the things you should know is that if you make your function have places where it's not well approximated by a plane, this can cause you trouble. So one of the things that's common to do is, well, you have an energy term and you say, oh, well, once I'm out of this distance range, then that energy term is 0. When I'm in this distance range, then it starts ramping up. If you're going to be using a minimizer that uses a function and derivatives, then it's really nice if those derivatives come in smoothly and or continuously and not just the function value itself. And this is, so I asked Matt for a good picture of this. So for example, hydrogen bonds in Rosetta. This is with 3 different data sets. The natives in red, decoys with a standard Rosetta scoring function, and with a smooth Rosetta scoring function that Matt and Andrew have been playing around with a lot lately. And these are the acceptor proton distances in angstrom. And this is sort of a histogram of how frequently features occur. These spikes here at 1.9 and 2.1 and 2.3 are coming because the hydrogen bond function changes regime, or it evaluates one polynomial in one range and another polynomial in another range and fades out completely in another range. And these were just sort of linearly interpolated from one to the next. And so there were kinks. You have a slope here and then suddenly a slope here. And so the minimizer will tend to pile things up right at that kink. And if you smooth that out, then you don't have those kinks. And it may not be so, I mean, it certainly looks a lot better when you don't have things piling up in these distributions, but you're also no longer underestimating stuff in this range here, purely because of the numerics in this case. So this is an example of an error in setting up the problem that will cause you to get different answers because you'll wind up in one of these peaks because of the lack of smoothness in the derivative. It's important to visualize, to see what it is that your program is doing for you and try to get an understanding. I mean, our visual system is the highest bandwidth channel we have for input. We have amazing pattern recognition abilities. Use it. Think of ways to draw pictures. So plots to confirm assumptions or that assumptions may not. So here's a plot to confirm an assumption that the donor type, the basic assumption in the H-bonds code was that donor type doesn't really affect hydrogen bond length. Is how the scoring for hydrogen bonds worked. And so if you plot in different categories, serine, threonine, and tyrosine in the blue, and the green and the red, you see that that assumption is not true. Okay, that depending on what type of donor chemistry you have, the hydrogen bonds lengths are different, and we've been trying to figure out exactly how to fix that. And that again is the one that Matt and Andrew have been working on. Be careful with your visualizations. I'm going to offend a bunch of people here, perhaps. Beware of visual lies. Okay, this is a lie. It's a very commonly repeated lie, but it's a complete. Especially if you put a path in here, it's a complete lie. Okay? Energy landscapes are not smooth. They're not 2-parameter functions with nice paths. Okay? What are we looking at here? We're looking at, so you can make a function that's an energy landscape that has only 2 parameters, say 2 reaction coordinates or something like that. But don't expect your minimizer to follow that energy function as it steps along, because what it's going to do is it's not going to have a minimum at each possible step of its, it's going to be floating somewhere above this thing, because really you're following a path in this huge high dimensional space. And locally, you're in a local minimum, but no way is it the global minimum for those particular reaction coordinates. So this path should not be following this two-dimensional surface here. You're in much higher dimensions. Yeah, I mean, formally you could say I've got, my landscape L of r and theta. Since this is obviously in polar coordinates, it's a minimum of f, r, theta, and 1,000 other parameters, if you're lucky. It's more, hundreds of thousands possibly. The path steps from local minimum to local minimum in 1,000 dimensions, and you're projecting it down onto this landscape, or you're taking a minimum to figure out where this landscape, and it's not you're taking a local minimum. So this is the curse of dimensionality. So the next quiz is what percent of a sphere in n dimensions, what percent of the volume is more than 1% from the boundary? So we'll take off this shell and just keep the inside. What percentage of the volume of the sphere do I have? In 1 dimensions, I've got 99%, or do I have to multiply by 2 or divide by 2 or something? But 1 dimension, I got 99%. 3 dimensions, 100 dimensions, 500 dimensions. So how far would I have to go to have only 50%, do you think? How many dimensions would I have to go to have only 50%?
1%.
Yeah, so the 1% shell actually has 50% of the sphere. Well, so sphere radius is pi over n factorial r to the 2n for even dimensions. And so if I take the radius with 1 and the radius with 0.99, what I'm looking at is 0.99 to the 2n in dimension 2n. If I put that on a long scale, so I start out having basically 1 in 1 dimension. And by the time I get to 200 dimensions, I have about 1/10 of the volume of the sphere is in the 99% core. So in 1,000 dimensions, it's less than 1/1000th of the sphere is in the 99% core. Everything is on the surface of the sphere. Okay? When you're in 1,000-dimensional space, nothing is close to you. Everything is as far away as it can possibly be. Okay? And this is what you're trying to optimize through and then project down onto a two-dimensional picture. And this is why the problem you guys are dealing with is extremely hard. You can do a lot of things in 1,000 dimensions. Okay? You have very nasty functions, and the pictures that we make of them are just complete and utter lies. Okay? You're going to explore a very small corner of this space. And so you've got to be, you've got to have some really good energy functions guiding you. And this is why it's not a surprise that you move over slightly and you're exploring a slightly different corner of space, because this space is really, really vast. The curse of dimensionality, let's see. The effects of, what am I trying to say? The effects of spheres that I was illustrating with that, sort of 99% core, it already shows up as an issue in 3 dimensions. If I take from the Kortem-Morozov-Baker paper on hydrogen bond distances, I take the data and I plot just raw histograms of hydrogen bond lengths, acceptor H distances. There's a peak where we would expect it for hydrogen bonds, and there's the second peak. What's causing the second peak? Is this a biological reason, or something structural? Why would you get a second peak? So we're looking at hydrogens with possible acceptor atoms and trying to measure the distances to see, they were doing it to try to figure out what sort of function they should use to weight these distances so that they will make a statistical potential. Why the second peak?
Overzealous crystallographers.
Overzealous crystallographers, putting H's too close. You'd think then they'd put them in the first peak.
There's like more pairs at longer radii.
There's more pairs at longer radii.
Regardless of whether or not they're actually hydrogen bonding, there's just like more atoms involved in
But why is it a peak? Then it should just keep going up. And I like using this as a qual question for biochemists because they'll come up with interesting explanations about, well, in a helix, maybe you're measuring from this hydrogen to the next thing around and stuff like that. And it's like, yeah. No, but you've got it. If you look at the number of points you expect in a sphere as the sphere grows, that's going to grow like a quadratic because the surface area is a quadratic. So, you take a uniform shell, make it larger and larger, the volume in that shell is going to grow as a quadratic. So if you had random points in space, what you would expect to see is a quadratic growth here, and you're seeing the beginning of the quadratic growth curve right there. Now, Rosetta cuts off hydrogen bonds when donor and acceptor are bigger than 3.6 angstrom. And so the donor and hydrogen are going to start getting cut off around here since the donor hydrogen link is about 1 angstrom. And so you're seeing now the cutoff that's coming in from cutting off the donor acceptor pairs at 3.6 angstrom. And so this is not a biological peak at all. It's perfectly explained by two geometric facts. One is the increasing volume in a sphere as the sphere gets larger, and the other one is the cutoff based on the donor atom when you're measuring the hydrogen atom, and then there's a little bit of slop because this can have different positions. And so visualizations can mislead you, and what you should do is, if you're expecting to see effects like quadratic growth in the number of points as your sphere gets larger, normalize by choosing your bin sizes appropriately, so that you expect the same number of points in each bin, and then peaks like this will stand out in the way that they should. And so think about the visualizations that you're making. Use normalization appropriately. Yeah?
Go into a little more detail about why that cutoff doesn't affect everything uniformly, and why.
Yeah, so we've got a situation where we're measuring the distance from an acceptor atom to a hydrogen atom. And we're going to do that only if the distance from an acceptor to the donor atom is within 3.6. And so the donor atoms with making hydrogen bonds are going to tend to be like this, and so we're going to tend to get the cutoff at around 2.6. But some of them will be out here, so some things go a little bit longer. And now these things aren't going to be affected by that cutoff at all, the real hydrogen bonds, because the donor is certainly going to be within 3.6. Does that answer your question? Or why does it not? It is affecting things uniformly. It's just that we're seeing a growth here, and it's getting chopped off. You're saying, why isn't this chop steeper?
Yeah, there's kind of like an underlying distribution.
Yeah, there's an underlying distribution because we're measuring to this point, and the hydrogen could be in anywhere around a sphere, right? And so most of them, if there really is some signal there, there's some angle cutoffs as well. But instead of cutting off at exactly 2.6 in this graph, which it would be if all of the hydrogens were pointing straight from donor to acceptor, we're going to cut off at slightly bigger values because this distance is fixed, but this position of the hydrogen is not quite fixed. So some of these distances get a little bit longer, which is why it's fading away here. Okay, that's more detail than I meant to go into on this, but It's perfectly explained by the curve up here and then the cutoff of that sphere. It's nothing biological. So again, be wary. Now, if you're dealing with things going on in high dimensions, samples in high dimensions, but what if they really lie on a lower dimensional set? There's been a lot of work on this sort of stuff. Again, the first answer is, well, try to linearize things. And that's what principal component analysis is. You try and find the best linear explanation of this cloud of points, and then project everything onto that. And then within that space, you've removed one dimension. Within that space, you find the next best linear approximation. And singular value decomposition will give you this sequence. And so principal components is heavily used because it's an easy analysis to do for a large. There are lots of other analyses, random projections, fast map, the L1 regressions to find small bases is really pretty amazing. When you're doing these sort of things, it's important, as I said at the beginning, to recognize what inputs are equivalent with respect to the algorithmic technique. So if you have a curled space and you're trying to do principal components, well, you're going to be fitting best linear components, and if you somehow know that the space is curved, you should try to normalize and take out that curve effect first. I need to keep going, so I won't say anything more about that. One of the things we do in computer science is we work from abstract models of computation. This is a Lego-based Turing machine. As computers, and the idea is, well, computers are increasing in speed and memory all the time. So by working on an abstract model rather than a particular one, we give our abstract model unbounded time, memory, and precision, which is one of my bugaboos. And then we try to minimize the time and the memory use. And so when you talk to computer scientists, you often talk about big O notation and the asymptotic running time of different algorithms. So log in. Binary search, looking in your phone book. N, anytime you have to go through a list of things or traverse all the edges in a graph or something like that. N log n, sorting, takes n log n if you do it by a good method like merge sort or quick sort. N squared, sorting if you do it by a stupid method like bubble sort or even inserting elements into a list. If you go to the end of a list every time and insert the element, like in a linked list, keep inserting at the end of the element, that'll take you n squared. Where inserting in the front or keeping a tail pointer will take linear time. And there's a big difference between n and n squared in the size problems that you can solve if you, the way I like to think about this is, well, suppose you give me 100 computers, or you give me one computer that's 100 times faster. Which of these algorithms make best use of the technology? How much bigger problems can I solve if the algorithms take these running times? And binary search, if you give me 100 computers, there's really not a lot I can do because the communication between these of coordinating the search would overwhelm the time. But if you give me one that's 100 times faster, I can now search lists that are 2 to the 100 times faster, 2 to the 100 times larger in the same amount of time. N is the ideal speed up. I mean, you give me a computer 100 times faster, you give me 100 computers, I can do 100 times more work. N log n, about the same. N squared, give me a computer that's 100 times faster, how much more work can I get done? Yeah, so 10 times more work. The square root of 100. N cubed, cube root of 100, whatever that is. 2 to the n? Okay, what takes 2 to the n time? Well, anytime I've got to make choices, and I could go A or B, and if I've got a sequence of n choices to make, and 2 options for each choice, that's going to be 2 to the n. There's a big gap between the polynomial and the exponential. These are basically intractable. N factorial is all of the possible ways of arranging things, n things, all of the possible orders. N to the n. I have n times, I have to make n choices each time. even with 2 to the n, if if you give me a computer that's 100 times faster, and I'm solving problems that are size whatever, size 100, give me a computer that's 100 times faster, I can just get a couple, 103 or something. I don't know. I should have done the calculation. So this is why we tend to talk about these things. And with memory, the cutoff is basically before the n squared. Things that are taking n squared memory, you try to want to avoid that if n is going to get at any size at all. All right. Now, from this abstract, there's a couple of departures from the abstract model to real computers. And if you know those departures, then you can write your programs and have them go a little bit faster. One is the memory. We don't have fast access to everywhere in memory. Memory is organized in a hierarchy, and you can think of, it's basically going to double in cost, in capacity, and in time to retrieve something each level, each step you go to. And so what you want to do when you're writing your program, store data that's used together. Because when you get retrieving things from disk or from further caches further out, it's going to retrieve a whole bunch of data all at once. You want to use all that data before it gets kicked back out to slower memory. And then the other thing is, use predictable access patterns. So if you're just going to linearly pass through, then that's what the computer is expecting. If you're going to hop all over the place, then it's going to read in a big chunk of data, use something once, and then have to read in another chunk of data. It won't be able to predict where you're going. Parallelization is another big topic. The really small bumper sticker is know your granularity. So coarse grain can be done easily on long-running jobs that don't need much communication. You just run multiple jobs and protocols. You do this all the time in Rosetta. You need load balancing if you want to get your full speed-ups, or you need a lot of jobs so that you can hide the imbalance. And you'd have synchronization barriers for communication. Fine grain, single instruction, multiple data, do the same operation to data in a stream is another good way to get parallelism. And GPUs will do this really, really fast, but you take some time to load data onto them. In general, when you're thinking of parallelizing something, think about the flow of data. Where is the data going to go? How do I need it? Where does it need to be coordinated before you think about the processing steps? And that's the next bumper sticker, basically. In computer science, we do a lot of characterizing problems by solvability, and I'm at the end of my time, so I should just, this is an example of a simple problem of. Matt was saying I had 9:15. When? Is it 9:45? Okay, good. Then I can go back and say more about this. Or I can finish up quickly and we can do something else instead. But any questions on these? I mean, so you've probably heard of NPhardness, right? So NPhardness is trying to get at what's the boundary between things that can be computed. There's some hope that they're tractable, that they take polynomial time, and between exponential time. And there are things that are worse than this even. In general, you have to take some of this for algorithms with a grain of salt, because usually when we're reporting times for algorithms, we ignore the constants, because the constants are going to depend on what kind of computer you're implementing it on, how good an implementer is actually doing the implementing, and these sort of things. And so these are reported for an abstract model of the computer, and will sort of hide some of the complexities to get an idea for how the algorithm is going to, how the time for the algorithm is going to grow as n grows. And it's part of the process of understanding what our functions are doing, is to analyze them and look at the time complexity that they take. when I actually come and implement things, then I worry a lot about the constants. And for example, the memory accesses is one big part of that. One of the ways I have of making other people's code go fast is to analyze the memory usage and restructure the memory so that things that are used together are stored together, because of the fact that, you know, if you have to pull things in from disks, you have orders of magnitude, it takes orders of magnitude much more time unless that is very predictable access. But I mean, this is one of my favorite games to play, and it really informs me as I do programming. But it's also, I guess, one of the best illustrations of the importance of algorithms for taking advantage of good computer hardware. Is MATLAB used to have a programming contest where you could take other people's code, edit it, and then resubmit it, and so a lot of people would tweak. You know, the running times would depend on a score and the time, the wall clock time that the code took. And so a lot of people would, you know, sit there, take other people's programs, do little tweaks to try to speed up the programs a little bit. And so the scores would go, the scores would stay about the same, and the times would go down, and different people would win. And then someone would come in with a new algorithm idea, and all of a sudden the time would increase again, and then people start tweaking again. All of the big drops were always because someone came in with a new algorithmic idea, and then tweak to speed it up again. So usually, one of the tweakers would win unless somebody had a good algorithmic idea that they just didn't submit until the last possible minute, and then nobody had time to tweak it. So it's an interesting contest. It was great fun for learning cute MATLAB tricks for how to tweak things and get things to go faster. And it was fun puzzles as well. Yeah.
Okay, so question. I remember reading in the review that Rosetta is NP.
Any problem worth solving is NP hard, at least. So.
So where does it fall on this kind of horrifying spectrum?
Yeah. So, well, I mean, you have to ask. You have to tell me what it is exactly. So that right now, that's not well defined. Do you mean finding the minimum with the given energy function? Well, that's not what it's trying to do, because it's trying to fold proteins, and we all know that the energy functions leave some things to be desired. So, but yeah, I mean, the basic thing of trying to optimize an energy function is going to be at least NP hard. Especially in these very high-dimensional spaces. It's a really difficult thing that you're trying to do. And it only gets worse from a computer scientist standpoint, because the way to do it is you keep bringing more and more biological information in. And the whole point of Rosetta is, initial point of Rosetta was, it's really hard to do this from scratch, so we're going to take fragments from all known proteins and assemble a library of those and use that to guide our search. And that works very well because at least you're making things that are locally looking like proteins. So it gives you a good starting point for your search, and then there's all kinds of things added beyond that to tweak. So doing that is going to probably make you even more local minima because of the way you start things. But it constrains your search to start with things that are closer to a possible solution than it would than if you were just doing things, leaving all the degrees of freedom free. So that's a win by incorporating more and more knowledge from the experimentalists' solutions of crystal structures. So in some sense, I mean, it's not worth talking about. What is it? I mean, is it NP hard or not? Oh, it's certainly NP hard. Anything worth doing is NP hard.
What do you mean by NP hard exactly?
Yeah, so okay. So what do I mean by NP hard exactly? So let's, all right. So, so this is one of my main tricks, is to know this hierarchy and exploit it. And parallelizability, like I said, it's a big subject. These are my bumper stickers. Coarse grain, use it. Think about it because you've got multiple cores on your processors now, and trying to do full communication, parallelism, something in between this is really tricky, and there aren't good programming environments for it. And so, if that's not your specialty, then let someone else worry about it. GPUs, wonderful things. Completely crazy architectures. Another PhD student that has been doing lots and lots of experiments for things that don't fit the GPU model well, like sorting and KD trees and stuff like that. And it's just amazingly difficult to figure out what it is that allows speed-ups. But the main bumper sticker is think of your data more than you think of the processing steps. Think of where the data has got to be processed when you're thinking about parallelism. Okay, so now let me say a little bit more about the idea of NP-hardness and these other complexity classes. We're really, in computer science, in the theory of computer science, we try to characterize the problems by the difficulty of solving them. And that way, if someone comes to us with a problem, we can say, oh yes, this problem is like these problems over here. They're extremely hard. We have no idea how to solve those. But at least I've told you something, right? So I can feel good about myself. And the person who wants to solve the problem walks away and mutters and says, well, what do I do? So the simple one is tile match puzzles. It's amazing that, just little variations on this idea of puzzles can give you different difficulties. So I found this picture of an Australian one that has beer bottles, where it's a set of 9 tiles. The output is you're supposed to match the tile edges and form a 3x3 square. And, well, you could, let's suppose I tell you which end is up on each one of these. Even if I didn't have any rotations, I've got 9 things. I've got 1 through 9 choices for my first one, and then 8 choices for the next one, 7 choices for the next one, and then just check if they match. Checking if they match is easy. I can just do that by visual inspection. Keeping track of all of those choices, 362,000 choices, that takes some bookkeeping, but this will be slow. Even if I'm doing it on a computer, I might actually be able to check all of those in under a second. But if we did a 4x4, then I'm looking at 2 times 10 to the 13th choices. 5x5, I'm looking at 10 to the 25th choices. And that's starting to get to take appreciable time, like longer than I'm going to live on the fastest computer and throwing 100 computers at it isn't going to help much. So it's you can make it go 100 times faster, but what's that to the difference between 10 to the 25 and 10 to the 23? It's not a whole lot. So you'd like me to say, oh well, here's the better algorithm, because obviously I shouldn't. Once I've chosen the first one, then I should only choose from among the tiles that actually match up with the first one. And so instead of having 8 choices for the second one, maybe I only have 4 choices for the second one. But even so, there's no way known of significantly reducing this from an exponential growth curve every time I add more tiles. Even though I can recognize a solution almost instantly when it's given to me, finding the solution is hard. And this is what characterizes this class of NP-hard problems. I can verify the answer, but to find it seems to require exhaustive search. Okay, that's the, there's a technical definition, and basically you can reduce one problem to another problem, that if you can solve this problem, then you can solve these other problems that are known to be in this class NP. So you can actually simulate computation using tiles like this. You can set it up so that you can solve there's many problems that can be solved by turning that into tile matching problems by constructing the right set of tiles. And that's the real definition, is the equivalence of these problems. So, simulating the solution to one problem by solving a different problem. NP-hard is actually good because it's solvable if you have long enough time. There are other problems that are just not solvable at all. In fact, the problems we would most like to solve in computer science, one is the halting problem. You would like to know, if you have a protocol and you run it, does it actually stop? Can you reach a certain threshold value? Can you write a program that will, when you feed it another program, will tell you if that program goes into an infinite loop? Or will tell you anything non-trivial about the program? Will this program print a 0 on the screen? In general, you can answer correctly for certain programs, but in general, you will not have a program that says that for every program. So you want to write a program that will tell if any program you give it can halt? Good. You write that program, give it to me. What I'm going to do is I'm going to add a little bit to that program. If it says it will halt, I will tell it to go into an infinite loop. And if it says it won't halt, then I will tell it to stop. And then I will feed my modified program back to your program. And now your program will halt if it doesn't halt. Okay, so it's sort of, Gödel said that any system that's strong enough to express the sentences that reflect on whether the sentence can be proved will not be able to prove all true things. And this is the same sort of thing. Any programming language expressive enough to be able to write a sentence that about the programs in the programming language, you will not be able to determine properties of a program in general. You can simulate programs with these tile games. If I give you a set of tiles, an arbitrary number of each one, and I ask you, can you make a snake path from point A to point B? I guess it's from point V to point W, where all of the things match up. Or can you make a snake path that stays above some line that you draw as the x-axis? This problem is undecidable. You can simulate the halting problem. This problem is actually decidable. You can actually answer that one. It seems weird. This one seems to have, has an infinite path all over the plane that you could fill up, and so, but this one you can decide, and this one with a boundary on it, you can't decide. It's a strange thing.
Well, I might have just answered my own question.
Yes.
But for the halting problem, you mean the compiled program, right? Not like the source code or something, because I assume at some point we'll have like a program that could interpret the source code and decide whether it should halt or not.
Yeah, it cannot. You will never be able to write such a program. I don't care what language, whether it's compiled or source code, you will never be able to write such a program because you'll just modify the program and feed it to itself, and it won't be able to decide. You can always see if a program halts by running it and seeing if it stops, right? But you may have to wait. You get an answer, yes, it halts. You may have to wait a long time. But if it doesn't halt, you never know. And that's one of the basic problems. So you would like something that will tell you, warn you, this will not halt, and so therefore don't run it. But you can't get that. There's no way you can get that in whatever language you use. Yeah. Anyway, so be glad that most of the problems, this is awfully like protein folding, isn't it? Problems are hard. And there's a rich classification of how hard problems are, and you guys are working on hard problems. That doesn't mean that specific instances can't be solved, but it does mean that there's a lot of cleverness necessary, and a lot of experimentation necessary. Yeah.
So two quick questions. So, am I correct in saying, in essence, the halting problem is asking, can you answer this question, or is it more complex?
So the halting problem, I guess I'm not sure I understand your question. So
okay. I'm not sure why this question 2, it seems to, does it halt or not? Is that the right?
Well, so here, this isn't a halting. I mean, this is only related to the halting problem in that you can actually simulate computations with this restriction. You can design tile instances that you'll be able to tile if and only if a program halts. Okay, so you can imagine that the tiles go wandering out a long ways and eventually have to come back. And the question is, as these things wander out, do they eventually stop and turn around and come back, or not? And for some reason, with that boundary there, you can simulate the halting problem. So you write any program, I turn it into a set of tiles. You play with those tiles. If you can make the snake, then I show you that your program must halt, is the way the proof tends to go. You reduce one problem to another problem. This one you can't. You can actually solve any instance of any set of tiles, so you can't do the same sort of converting halting problems into tiling problems. It's a strange thing. All right. So when you look at your algorithms book, you see lots of problem-solving approaches. These are mainly focused on the polynomial time space, the space where we know how to solve problems efficiently, with a few exceptions down at branch and bound here. Brute force, try all possibilities. Well, that's something that can take exponential time. And it's actually a good reference from implementation. So start out by just doing something simple like that on small-sized test sets. And then use that for your unit testing to make sure that when you go to more complicated algorithms that you get the same results. Divide and conquer is a standard computer science technique. Split problems into separate subproblems, solve each subproblem, and merge the solutions. This only works for problems where you can split them up into two separate subproblems that don't affect each other. So these things happen down inside of Rosetta, but the whole problem Rosetta is trying to solve is not going to be of that form. Incremental, grow things and maintain a solution. Greedy, build a solution by making the locally best choice at each step. There's a certain class of problems for which that will be the globally best choice in the end, but for most problems that will not. But that's often an easy way to start and get a dynamic programming is been rediscovered many, many times. Bellman was working for Rand Corporation, and he liked playing with algorithms, but they wanted him to do more serious engineering. So he had to come up with a name that made it look like he wasn't doing algorithms, so he called it dynamic programming. Because, it's like programming as in computer programming, and it's dynamic. And it's the worst name possible, and it's stuck. He admits that it was intentionally chosen to be confusing to his employers. But it's basically, you're going to solve an optimization problem by assuming that all of the smaller subproblems have already been solved. And then you use the magic of recursion. And so you need to solve problems at the bottom level, and then you build up a solution by taking the best possible solutions. And there's a lot of dynamic programming that's used in the area of trying to optimize things for optimizing scores and things like that. And some people have built, Hellinga is built on dead-end elimination. It's basically built on a form of dynamic programming. Branch and bound, you've got a bunch of possible choices. You imagine making each one. You could do this in parallel if you've got a parallel machine. You branch on the possible assignments, and then you do some rough evaluation and communicate a little bit and kill off the ones that are surely not going to lead to a good solution. So you want both a way to quickly estimate how much the solution is going to give you, and then you'll refine and go down the tree and branch the solutions that seem most profitable. Very effective technique. And the problem, I guess, I have to apologize for people that teach algorithms like I do. We focus on the things that we can solve and these techniques that lead to solutions of the polynomial time problems. When we get to the NP-hard problems, I'll get to problems like Rosetta, we have already been saying that the way to solve that is to bring in a lot of domain expertise. And so we don't have that domain expertise, nor can we generalize how to bring in that domain expertise in a way that will work for all problems. And so we don't focus as much on solving the NP-hard problems in the basic algorithms class. And so when you take algorithms, you'll hear a lot about this, and in the end of the class you'll get to dynamic programming, and maybe they'll say something about branch and bound. But then if you go read the literature, you get all kinds of other techniques. Intelligent optimization techniques, sometimes called search recognition clustering. There's no magic bullet for NP-hard problems that you still want to solve, which includes everything interesting that's not completely intractable. So you get Monte Carlo, Metropolis, simulated annealing, genetic algorithms, taboo search, particle swarm, neural nets, SVN, k-means, or, my biggest problem with, as an algorithms person, is people come to me and say, oh, I solved this by a genetic algorithm. That tells me almost nothing. That's telling me the procedure, but it's not telling me how they defined the problem. Okay? So, a simple example is, image recognition. I want to recognize, do an image search or something. Okay. I got to come up with what is my representation for an image? How do I decide which images are similar to other images? Well, one way is to say, let's just take a histogram of all of the colors appearing. And anything with the same color histogram is using the same colors. And so here are several images that are using the same color histogram. And I could scramble this much more and make it look, obvious that it has nothing to do with the Mona Lisa, but keep all of the pixels the same. The fact that I just use the colors and not where those colors are located means that all of the images that use the exact same set of colors, no matter where those colors are all going to get the same score. And they're all going to be classified into the same class. And these are the sort of things that you need to think about when you're dealing with, these are called intelligent because they often need and convey no human intelligence. All the intelligence must be in the algorithm, therefore. No, the technique is less important than the problem representation. Okay? If you've got a favorite technique, that's fine. But before you tell me about what the technique is, you have to tell me what the problem representation is. Image histograms, it's not so good if you think that people are going to start morphing your images by just moving the pixels around. So you have to consider how the algorithm or how the representation partitions all of the possible inputs into different classes that are equivalent from the perspective of the algorithm. So for example, if you use bond angles, then whatever you do is going to ignore packing constraints because you can't determine the packing from just the bond angles without actually reconstructing the thing and then using a different thing to do packing. So anything where you're using bond angles and handing it to a neural network, it's not doing reconstruction, it's just using angles, it's not evaluating packing. Okay? Which is fine if what you're looking at doesn't involve packing. But if it does involve packing, then you need to think and see if there's more that you need to add. All right, so wrapping up, whatever you do, make it correct first and optimize later. Build a simple reference implementation and some test data. You're probably sick of people saying things about testing, but make it work early and often. Compare results with your later, more complex implementation. But the benefit is you get the satisfaction of completion over and over again. Proofs and Refutations is one of my favorite books on, since Andrew mentioned he was a philosopher initially. Favorite books on what does it mean to do mathematics? Are you just trying to do proofs? No, you're also trying to find counterexamples. And really what both of these are working for is understanding the definitions. And in the same sense, when you're coding and making test sets, you're also refining the definitions of what you're trying to do by working at it from both ends, by making the constructing the object, but also constructing the examples, the counterexamples that, on which things that are close to the program you want but not correct are going to fail. And so work on both the proofs and the refutations. I guess final bumper sticker. Any questions? Yes?
I have a question. So, well, it seems like you've convinced us that maybe what we should do is just work on really, really, really used models of proteins, with really, really, really simple functions, so we can at least find the minima. And you've thoroughly convinced me that we'll be able to have any hope of finding any global minimum ever for a real protein. So what do you think?
Well, it sounds like you got to work on small molecules that will address depression issues. So, but yeah, no, I mean what I'm trying to say is understand the tool that you're working with. Okay, you want to if you want to use a tool well, you have to understand, that hammers are meant for nails and not for thumbs. You're dealing with you're trying to do a complex task, and so you need complex tools. And the complex tools, there's a lot you can understand just about the tools. And so some people like me get hung up on just understanding the computers and never actually worry about using them for anything useful. That's not entirely true either, but this is the difference between science, where you're going to go out and try to understand things, and any little bit of understanding that you can get is useful, and the computer science, where we're creating something new. What's happening in the protein folding is you're sort of in between there. You're trying to create new folds, and then you go out and do science and say, does this behave the way I think it behaves? And so you have the opportunity of, constructing things to probe nature, as well as all the experimental techniques used to probe nature. There's no reason you shouldn't try to do big things. Just understand what you're doing as you're doing it. Realize that it's hard, and don't go ask the computer scientist for a magic bullet, because it's not going to come. Which means that you're trying to find what is the piece of information that you can extract from the knowledge that you've learned, or that the whole community has learned, that can be fed into the computer to have the computer results be better. And to me, that sounds like an excellent collaborative project, because a lot of people have to bring in a lot of different information, and that's one of the reasons that working with Rosetta is so much fun. It's that everybody's winning, everybody's happy to talk to each other, and so it's pretty intense. So don't get depressed. Yes, I know you're not. You're just kidding, but.
What are the things at this point that we can do well in terms of protein design?
Mm-hmm.
There's a lot of things that the scale is doing, but what are the sort of the building blocks that we can use to solve more complex problems?
So what sort of problems do you want to solve? I mean, so it's the CASP competitions are fascinating to watch. Big strides from the fragment libraries, and then the structure of the and then things slow down because people things become harder to get to continue the advances, and then you see ideas coming in the next competition, like what is Zhang's use of larger fragments to sort of, when you've got something, then you look for larger fragments that can substitute for it. These are examples of things putting more and more domain information in to polish up the final result for the CASP contest. Okay, whether that's the right thing to be doing, and then you got other people like the Richardson lab looking at the scoring for the CASP contest, saying, well, let's put on all the hydrogens and now let's see what happens, you know. What are the things we can do well? I'm the computer scientist. I'm not sure I can answer that. But to me, it seems like the thing that Rosetta is doing well is that it's taking both people that are using it for design and people that are developing it, and they're working together trying to make a tool that can be effective. So it's not like they're trying to automatically do everything or by hand do everything. These things are converging and are informing each other. And that, I think, is the part that shows the most promise for things, is people bringing their different expertise around this large and sometimes unwieldy software tool. But I mean, you got so many people that are using it to try and design proteins or docking or something, doing docking studies, that if you're a developer and you break something, you hear about it right away. People care about this thing and where it's going. So, yeah.
Just to build on what you said, but maybe I'm from experimental background, so
Yes.
I think it this way, that we all know that it works. Protein folds, and protein knows how to fold. So there is a solution, but Rosetta, and for that matter any computer, can only do that much with the information given. But experiments don't have this limitation. Over time, experiments will keep telling you things, and hopefully keep telling you more and more information, and that's priceless. And as you feed more constraints, more information to Rosetta, the more things that you tell the information on, the better it will get, and eventually I'm pretty sure there is a solution at the end. I mean, it maybe it's a bit far off, but there is a definite solution which we can definitely get to.
It's not necessarily true. There doesn't need to be one general solution.
Oh yeah, I mean, there might be but we can at least arrive at a consensus that, okay, this is probably how it is doing, and I mean, so the idea is to best get to the protein folding or design things as close to how nature does it, and that's the idea. I mean, nature does it, so there has to be a way it does it.
And that's, Rosetta is not doing it how nature does, and nor should a computer necessarily do it how nature does. I mean, the computer is going to have different strengths, and is going to solve things in different ways, I think, always. And, you know, this reminds me of Lewis Carroll's Sophie and Bruno, where they decided that they wanted a map, and so they decided that bigger maps are better, and eventually they got the 1-to-1 scale map, and then they decided just use the countryside as the map. I mean, we understand things through models, okay? Computational models they're always going to be approximate. Our understanding of how nature folds proteins is always going to be approximate, because if we say, oh yeah, this atom goes here and this atom goes here, that doesn't give us any information, but doesn't give us understanding. We're going to understand it in terms of a model. That model will have a computational component in it, because that's the way our models are these days. And so if we're looking at, you know, being able to explain how nature folds proteins, that's going to be probably a model that's a lie, okay? But it will be a lie because it's better at explaining things, but something we're better at understanding.
It tells me in the end pretty much, I mean, even if it goes through all the lies, but arrives at something that makes me feel, like, okay, that's how it is.
Yeah. So I should stop and turn things over to the next one, right? Tim is going to do constraints. He's going to.
We can take a quick break.
Yeah, okay.